All right, well, Kevin, so this is the last mini-sode. I know last week we talked a little bit about CubeSats and their subsystems, but today we're going to talk about mission planning, right? I mean, like once you've made your CubeSat, it probably has to go through quite a process to actually get it into space. So tell me a little bit about like once we've created and assembled that CubeSat, what are our steps?
Well, first of all, we're going to go through the mission life cycle. So we're going to go through the process by which you would come up with the idea through the operational phase. And there are a number of steps, a number of checkpoints, and in fact, a number of stakeholders that you have to be aware of. So let's jump right into the slides. So this is this section or this lesson is called Future CubeSat Mission Planning. So as you are preparing your CubeSat, let's look at some of the important steps along the way. Okay, so first thing you need to know when you design your own CubeSat mission, especially if you're an educator, someone outside the normal NASA or aerospace engineering industry, you're going to have lots of steps, lots of process steps along the way. And some of these are sequential, but some are running concurrent. So it's important that you really make a great timeline for your team. And you can use the NASA Systems Engineering Handbook to help you set up your mission in phases, beginning with pre-phase A all the way through your closeout. Make sure you lean on the First-Time Developers book by NASA and a network. Find a group of engineers and folks that have knowledge or work in NASA that will help you.
Yeah, no, you mentioned last week the CubeSat 101 book. So is it kind of like a workbook or a handbook, if you will, that kind of walks you through all these same steps?
It is specifically a first-time developers book, especially for those that are maybe unfamiliar with NASA's way.
How does one get these? I mean, or you have to go to Amazon? Are these available online? Or
no, originally a nice lady at Kennedy Space Center shipped a case of them to me at SmallSat, but now it is a PDF. If you simply Google NASA CubeSat 101 PDF, it will be your first hit. You can download it.
So it's free.
Absolutely. Absolutely. So I also want to mention, in addition to the sequential and concurrent steps that you have to complete, that you are going to need to coordinate with a number of entities. So I made a list, and there may frankly be more, but we're going to talk about your suppliers, the folks that you'll end up buying your parts from, your integrator, your launch provider, test facilities, the Federal Communications Commission, NOAA, which is inside the Department of Commerce, and possibly NASA.
It's so funny that it's in the Department of Commerce because you think about weather with NOAA, right?
There is, yes, there currently is a legislative effort to remove NOAA outside the Department of Commerce, but we'll see.
So I would imagine, like when you're dealing with anything governmental like that, that there's a lot of red tape that can go along with getting these certifications. Because they do other things besides CubeSats, right? Obviously, the FCC we're talking about all communications, but this must be a small niche for those.
Yes, I'll be speaking about the FCC later, but they control all non-federal government uses of the electromagnetic spectrum. So, and it's very important you get your coordination done properly, or you could be demanifested, meaning you've earned a ride, been assigned to a mission, but you'll be taken off of that mission because you did not have your paperwork done in the right way.
It looks like it could take a lot of time. That's probably why these take a little bit. It's not like a 1-year thing. I know you'll talk about the timeline a little bit more, but it seems like with all those people involved, it could take a lot longer than you expect.
I really believe if you've never built one before, you're going to need 3 years. I think the more you build, the more efficient you get. And really, it depends on whether or not you're having to raise your own money. So that's important as well.
Well, and then by then you probably have established the companies that you want to work with, your suppliers, your integrator, your launch provider. You probably already kind of have somebody once you've done it more than once that you trust and that you want to go back to.
That's exactly the way it's been for us with the Wolfpack. We found a few companies that we really trust, and they're good to us. and it makes it easy to go back to them.
Do you meet them at these conferences like SmallSat? I know you just got back from there. Is that where you tend to meet a lot of these suppliers?
SmallSat is a great time of year to not only meet your people, but also examine and meet some new folks. So yes, absolutely. SmallSat has probably 4,000 CubeSat, SmallSat folks at one place at one time. All right, let's jump into it because we've got a number of steps. This is a notional timeline. I recommend at least 3 years for a pre-college mission. You can see the Gantt chart shows a number of sections that you need to complete. And you can see obviously that some of the bars vertically overlap with one another. So those would indicate concurrent activities.
So just as a reminder for those who are listening on the podcast, you can see the actual visuals by going to our YouTube channel at Aerospace and Innovation Academy and checking under the podcast playlist if you're interested in coming back and seeing some of what he's saying. But so, yeah, I mean, that looks like, I'm not going to count them, but it looks like a good maybe 10 different steps in the process that you're kind of backwards planning with a lot of that, like that mission coordination in the middle of it seems to take up the most.
Absolutely. Around the time of building, licensing, and your weekly tag ups with your integrator, those are all big blocks of time. So let's jump into them individually. So at first, you're going to develop your mission concept. As we tell the kids, you've got to know the very first thing you need to decide is what is the reason that you need to go to space. So when you're developing your mission is going to determine what your payload is. And the payload, the experiment or the work to be done by your payload is the reason you are going to space.
Right. And I think that was episode Minisode 2, where we talked about the different kinds of payloads, like biological or communications, right, things like that.
They're almost immediately, you need to be thinking about how are you going to fund your mission, particularly if you are applying for NASA's CSLI. There's 4 specific areas of funding that you are going to need to be aware of. Of course, your materials, your hardware, if you will, for your satellite, but labor, you may very well need some labor if you're going to get some help from outside companies. Your travel, you'll be required to travel for a mission readiness review and to collaborate or to partner with your other entities. But and most importantly, at the end of the design and test lifecycle, you have to do environmental testing.
Well, you have to actually pay for your launch too, right? Like,
unless you are a recipient of the NASA CubeSat Launch Initiative Award, then you definitely do have to pay for integration, testing, and launch. Now, NASA has covered that for us before, and that's pretty common if you are selected through their program. Just going back to the testing that you'll have to do, there's 4 kinds of testing. There's several kinds of testing depending on the integrator and how you're getting to space. But at a minimum, you can expect to do acceptance testing and vibration testing, thermal bakeout, where you heat up your satellite to measure the mass loss. It's a great way to see how many volatile materials you have. And obviously your radios and batteries and lots of other tests.
With the vibration test, I think you alluded to either with the payload Minisode or the one from last week, but you want to make sure that it's simulating what it's going to be like during takeoff so that if parts don't become disassembled. Is that right?
Yes. Every launch vehicle has some fundamental frequencies based on the type of engine and the kind of vibrations that are going on in the combustion chamber and as a function of the aerodynamics and the thrust. So you want to make sure that nothing about your vehicle will resonate or amplify the vibrations that you would expect with your launch.
I think I've seen some of these. They're like tables that shake really fast, right?
That's right. There are shaker tables, yes. So funding, I can't stress it enough. It's as hard for me as literally building the satellite is trying to make sure we have money in hand. Now, what's important when you're raising your money is if you're going to apply to NASA for a launch, you have to have money in the bank before you apply, or you are automatically disqualified. That's an important criteria to remember.
Is that because they don't want to give a ride or at least the idea of a ride to somebody who then can't bring or deliver the CubeSat eventually
Right.
to them?
You don't want to waste a slot on a team that wasn't ready when there might have been teams that were better prepared for launch. Okay, so step 3, NASA requires, prior to your submission, a merit and feasibility review. Simply put, you need to get some outsiders, some folks that aren't part of your team, and you need to have your project evaluated in 2 ways. When we say merit, what they're really saying is, does your investigation support one of NASA's strategic plan aims? Are you hitting some note that in their requirements for advancing science, education, technology, or operational goals?
Oh, I think I've seen that in the handbook where they kind of list out and you, because I think I remember seeing your report, right? Because you almost have to do like a big write-up on how you met the requirements.
Well, that's
of these
coming up.
things.
That would be our actual submission
I got
to
it.
the response. Our response is our proposal to NASA.
But it's got to meet some of those feasibility things, it
Absolutely.
sounds like.
Best advice I can give you. So if you're taking notes, this is an asterisk moment. Make sure your language matches NASA's requirements. It is difficult. It is more difficult for them to say you did not hit the mark in a certain area when you are parroting to them their strategic aims and goals. So that's the merit review. So
is that where you have to also like get when they have to go through that process where they're presenting and you have that like,
well, that's we do that
design review or
right.
something?
That's we conduct our merit and feasibility reviews at the same time during a preliminary design review. Right. And that is well known within the systems engineering framework of the life cycle of a project. And you can learn more about PDRs and all the other reviews through the NASA Systems Engineering Handbook. So real quickly, the feasibility review is simply not about your mission hitting the notes that NASA requires, but is your proposed mission, is it feasible? Right. Can it be done? Is your mission resilient? Have you identified risks and mitigated them? And do you have a reasonable probability of success? I have no doubt that amongst the 10 or so proposals we submitted, some were great ideas, but we did not have the team put together to carry out such a complex mission.
Well, I think that would make really good sense. And in your PDRs, it sounds like they would probably be asking up some of those questions that would make you think about, hey, we got to rethink this design, or we got to think about how this is going to work. So that helps you to make it more feasible. Yes.
Right. So we conduct our PDR, our feasibility and merit reviews within just a few weeks of submitting our ideas. We've tried to really work through the process, and having done it a few times, but we take your reviewers' comments and not only do you list what their comments were, but you show in your proposal how you adopted the recommendations. That, I think, is a strong way to improve your proposal. So now you've done your merit and feasibility review. Your reviewers have given you a thumbs up that this proposal should proceed. You then spend 1 to 6 months, you're designing your CubeSat and preparing your proposal for the CubeSat launch initiative.
And when you say designing your CubeSat, are you like designing these in like a CAD drawing thing? Or are you actually like 3D printing, or using some kind of chassis like you had mentioned before?
Well, you're going to be doing all of the above, but think of it as designing the recipe, if you will, the concept of operations. You'll work on your concept of operations. You will work on all your hardware. You'll work on things like a power budget, a data budget. You'll make sure you're within the size, the mass, and the power requirements. Your cost, cost is often a factor. If you think about it, your satellite will only have the ability to generate so much power. So determining how you allocate the current that the batteries can send, or the voltage, that's important. That's called the power budget, to make sure you're not trying to run a dryer on basically a 9-volt battery.
So like all these sections, these steps that you're talking about are probably in that CubeSat 101 handbook that you probably just kind of go in sequential order, and it kind of walks you through that process.
Absolutely. I liberally drew the notes for this presentation from that document and a couple of others. So again, it's a great developer's tool.
So the design is different from the actual development. Is that correct? The design is just kind of like the thoughts, getting them down on paper, and then you're building it.
For us, we like to lay everything out on paper as much as we can, and we don't want to spend our money until we're selected, because our money is so hard to raise. So when we say designing your CubeSat, we're talking about CAD models. We're talking about all of that associated paperwork. All of that becomes part of your submission to NASA's CubeSat launch initiative. It normally comes out during the week of SmallSat, early to mid-August. And then the due date for that response for a proposal, a call, if you will, for NASA for proposals, normally is the first week of November. So from November to March or April, let me share a few thoughts about designing your CubeSat. NASA gives you some great advice. I will share 6 simple points that should increase your chances of success. Number 1 is to always keep it simple. Don't try to overcomplicate your mission. I often try to de-scope the students because they have very exotic and imaginative missions, but we need to always keep in mind our constraints of power, mass,
Size,
money,
weight.
budget. Yes, mass and power and size. Yes. Secondly, in addition to keeping it simple, keep the most important components close to the exterior if you can, so that if you need to make modifications or substitutions or replace parts during testing, you don't have to disassemble a lot of your vehicle. Also, don't push the performance envelope. You have limited power, data budget, mass, size, all of those constraints we've been mentioning. Don't try to push the limits, especially on your first mission. Keep it simple, keep it within the parameters that you're given, and then increase your chance of success. All right, often our CubeSats will have deployables, either batteries or solar panels. NASA recommends that you use redundant wires. We literally use monofilament fishing line to hold antennas and solar panels down until you're deployed into space from the P-pod or other deployer. And at the right time, what will happen is you will send current through a resistor that is touching your fishing wire, and the fishing line will be melted, which will allow your components to deploy. There's always a chance for something to go wrong, and being redundant is just good engineering practice. So NASA recommends, and as do I, that use redundant lines, fishing lines or monofilament lines to hold down your deployables.
So when you say redundant, to make sure that you're doing more than one, to like
have more than one in case one
doesn't
breaks
work.
or comes loose. Yes, during the ascent.
But if you have more than one and one is fine, like one is melting, what if the other one doesn't?
Again, then you would have multiple resistors touching the wire. So you would have.
I see what you mean. So like even if it doesn't ignite on one end, it's going to ignite somewhere else.
So if you have multiple resistors on your wire, you could send current to them sequentially.
So you have like 2 points that like at least one of them will be activated. If not.
Yeah, multiple wires, each with multiple resistors. Additionally, NASA, it's always good practice when you're designing your CubeSat mission to use components with flight heritage. NASA has something called a technology readiness level. 9, it runs from 0, where you and I might dream up a component and draw it on a napkin in a bar somewhere, versus TRL 9, which means it is flown to space successfully and is proven. Use components with flight heritage whenever possible.
So flight heritage means they have experience, that they have credibility.
And they've been shown to work.
Right, credibility.
Yes, there's no need to introduce even more variables than necessary on your first mission. Lastly, use UL approved batteries. UL stands for Underwriter Laboratories. They are well known for their ability to test and make sure components have a certain level of quality and reliability. So use UL registered or tested batteries to ensure just one less headache as you move your mission along. And lastly, avoid using materials that have high melting points. You should lean on the NASA documents to make sure you don't use any materials that are going to get you automatically disqualified from the flight opportunity.
What are some of those that would get you disqualified?
Metals that are very, I always think of tungsten. Tungsten is it's an incredibly dense metal, and it has a very high melting temperature. So you don't want any metals or materials. Aluminum is acceptable. Others are not, because they may reach the earth. They may not volatilize as they burn up in the
they won't burn
atmosphere.
up to come down. They can be a hazard.
We need them to burn up and not, reach the earth. So you've submitted your proposal to NASA in November. Let's say March or April, you get a good call. You get a great letter from NASA that says you have been accepted into this round of CubeSat selections. Afterwards, you will begin something called mission coordination. This starts normally with a kickoff meeting between you, some NASA folks, maybe a launch provider, definitely your integrator. So if you want to think about the job of the integrator, they hold your hand as you move from being selected by NASA for CSLI until you have fully deployed your spacecraft into the deployer prior to it being mounted on the rocket. So there, you want to play nice with them. Listen to them. They tend to have a lot of experience. They can really help you be successful.
So it's like your wedding planner. Like if you're going to have a wedding, somebody who's like getting you from point A to point B.
One of the most important things you should get at or around the time of your kickoff meeting is an ICD, an internal control document for the integrator's deployer, or if it's another company, that company's deployer. So that ICD is going to give you a number of checklists, and it's going to give you a step-by-step pathway that you have to follow very closely. So as you are now coordinating and beginning your mission integration or your liaising with your integrator, you want to start working on getting your license. So as we mentioned, there's at least two kinds of licenses that you'll need. If you are collecting any kind of imagery outside your spacecraft, you're more than likely going to need a remote sensing license that is controlled or authorized or distributed by the NOAA, which is within the Department of Commerce.
Is that the one that Elon Musk got in trouble for?
Yes.
He didn't have their permission.
He flew his Tesla Roadster with that mannequin, and the Earth was in the background, so he was remote sensing the background, but he did not get a license, so he probably paid a hefty fee. So
because the picture of the Earth in the background, he
was capturing imagery of the Earth, and that's the rules. So get started on your license early. Of course, it's a government entity, so there's paperwork. So just get on it.
Okay, but wait, I want to know why taking the picture of Earth is it like from a military or defense perspective that we don't want people to take pictures of the Earth because there could be safety considerations?
I think that is one way to identify who, I'm just speculating here, but it's probably one way to minimize any kind of stealth players or any kind of espionage or spying.
If astronauts are in space, are they allowed to take photos?
That's not a spacecraft. They're people, and the ISS. I don't.
Okay, so this is for spacecraft, not people taking who are in spacecraft.
Yeah, Musk got in trouble because he was taking pictures of his car and mannequin, but the Earth was in the image, so he was imaging the Earth without a license. All right, so the FCC is the Federal Communications Commission. This license, I believe, is harder to get than the remote sensing license. The Federal Communication Commission controls all of the use of the EM spectrum except for the federal government, which is controlled by the National Telecom and Information Administration. So the FCC is another entity that has been very difficult to deal with. And frankly, it's not always their fault. They had a smaller office, and we've gone from, 5 satellites a year being launched to thousands, and it's simply overwhelming. So my recommendation is find a company with expertise in working with the FCC and just pay them a fee and have them help you secure your radio license. We have done that successfully twice. And if you reach out to me, I will pass along this really great guy who can help you liaise.
Well, I think we did a podcast interview with him.
Yes,
a while back.
so
these are like brokers, almost like within the industry that can kind of do the work for you and maybe expedite it. It's like
it's definitely they're assisting in the process.
It's like when someone meets you at the airport and walks you through.
Right, exactly. And since he is one of our podcasts, I would encourage you to go back and find a podcast we did some time ago, probably in 21 or 22, with Michael Miller, Mike Miller of Stirk Solutions. Just listen to that podcast. It's a very informative. It is so important that you get your radio license, because you can be removed and lose your flight opportunity if you are unable to get a radio license.
And that's the part I remember talking with him when we were at SmallSat too. It takes so long, even when it's in the process, that because they're backlogged, because the sheer number of CubeSats now versus what people were putting up when they first started, like the timelines for these, they don't even have enough people to like run through the paperwork, right?
Right. And on our first mission, we would have potentially lost our ride had it not been delayed several times, because we had some difficulty getting our radio license. So that's became very evident to me. And I want to encourage all of you, if you're working on your CubeSat, get to work on your paperwork for your licenses.
As soon as you're accepted, I would say, right?
As early as possible. Yes. So we're moving along now. You've been selected. You're meeting weekly with your integrator. You're working on your licenses. And now it's time to start working on the specific documentation that you're going to need for your mission. And that sort of concurrently goes along with building and developing your ground station and fabricating your spacecraft. So all of these things are going on concurrently.
When you say building your ground station or whatever, because that's where it's going to receive your telemetry, right? Or your information that's being sent back. It's not like a station in the way like we might imagine, like it could be a computer, right? Like,
so most ground stations, it could be as simple as an antenna and a radio, an antenna and a radio. And that radio could be quite small, even a Yagi antenna made from bimetallic, like a tape measure. But I was going to let you know there's a couple of options when it comes to your ground station. I chose to use a radio that talked above us. We were in an orbit below a network of satellites called Global Star or Iridium. So I chose to use those because there were 24 Global Star satellites. They were at 1,100 kilometers. We were at 550 kilometers. So our satellite could always see some of those satellites and talk to them. And then those satellites relay data down to the ground, to a ground terminal that is then shared with us on the internet. So that made it a very, I de-scoped the mission to be more successful. And I did that on purpose. So let's say you built your ground station and you've tested it. If you're going to make your own ground station, those can be tricky and tough. And those can eat up a lot of time. So plan ahead if you're building your own ground station, and as you coordinate to make sure how your radio speaks or communicates well with your ground station. So you've gotten your internal control document from your integrator. You are going to review it and make sure you see all of the tests that you have to pass, the flight certification documentation, before you're ever allowed to integrate your spacecraft with your integrator. So it's very important that you be timely in submitting your paperwork. You leave time to rerun a test if something fails. But the bottom line is you want to hit the date when you need to integrate, even if it means your spacecraft sits on the shelf for 3 or 4 months as you wait for the rocket to take off. So now we built our satellite. We've tested it. We've submitted all the paperwork. The last thing we're going to do is a mission readiness review. So a mission readiness review brings the principal players together, and you as the team lead or your students need to be there at the location designated by the integrator, and potentially NASA and others are there. And you're going to assure them you know, you're going to look through the ConOps and all of your paperwork and all your documentation, and you're going to be certain that you're ready to go for launch. So this is your last, it shouldn't take more than a half a day. It's really to show that you've met all the requirements in the ICD or the internal control document.
What's ConOps?
Those are your concepts of operation. Concepts of operation are simply, think of it as a flow chart of activities that happen in sequence. So, you know, your ConOps might begin, you know, satellite is deployed on orbit. The internal clock begins once the pins aren't pressed in, the electrical inhibits, and your CubeSat powers up as soon as it's deployed. But then NASA requires that you wait 30 or 45 minutes before your radio turns on. So it's sort of a sequence of events. And then imagine once you have normal operating mode established with your satellite and you have communications with it, then you're going to have a set of procedures of your experiments that you're going to run on orbit. So you need to make sure that all of that is clearly thought out. So finally, the day is here. This is a big day when you go to your integrator. We went to Seattle for one, and the second one was in Houston, but we go to Seattle. I took 6 middle school students and they integrated the CubeSat. So what they're doing there is they're doing the final checks, final tests, and they're loading it into the deployer. And this deployer is going to be mounted on the top of a Falcon 9 rocket. That's a huge day.
Is it always a Falcon 9 rocket?
Oh, no, it just depends on what your ride is. The second CubeSat rode in probably an air-conditioned Pelican case, you know, foam, a nice cushy ride all the way up to the ISS, and then it was kicked out.
And then this most recent one is going to be on something that is called a Vespa ring. Is that right?
Vespa ring, yes.
Not a Vespa, that's a
our third mission is
scooter.
actually a hosted payload, which means we're simply riding inside another device. So that's a hosted payload.
Maybe the Italians send up a Vespa ring. Come on, that was good.
No.
It was fun. It was.
So let me tell you the most exciting thing about completing integration. From the educator or the team lead and the student standpoint, once you satisfactorily complete integration, you cannot mess up anymore. It's now out of your hands. You have done everything you can in this mission, and now it's just up to the rocket. You know, you're hoping the rocket doesn't blow up, and next thing you know, you'll be in orbit. Then the next thing you want to think about is, does my radio power up? So that if my radio powers up on orbit, then my satellite is alive. So once your rocket launches, then you begin the operational phase of your mission. And it's important that you analyze your data. And then you need to have accounted for how you're going to decommission your spacecraft. There's a lot more emphasis on eliminating or mitigating debris and making sure that your vehicle is not going to pose a threat to anyone else.
That's
as it returns.
deorbiting, right? Like that's,
Right.
you know, you're going to
Deorbiting. Sometimes with the big communication satellites, they're out at geostationary orbits. They're, I want to say about 38,000 kilometers, whereas we were 500. At that altitude, you just take the last bit of fuel and push it even higher up. So it takes, you know, 10,000 years to come back to Earth. So that's one way to decommission. But primarily, if you're low Earth orbit, you're definitely going to deorbit. And then for us, those of us that have received the CubeSat Launch Initiative, your very last step in this process, you want to write a bunch of papers, you want to get your kids published and talk about your project, speak at conferences, but NASA is going to require a final report. And that really is a little due diligence, you know, helping making sure the taxpayer is justified. And it's a nice way to bring your students in one more time to be involved with the writing up.
When they can like talk about what went well. It's like the after action review, I guess. We're like, here's what we did. Here's what we would do differently.
Absolutely. It's always a very satisfying thing to write your final report. And so, my friends, that takes us through a number of steps from having an idea to the end of your operations. So for those of you that are going to go to our YouTube channel, I just threw in a couple of pictures from integration day of the YSAT with the middle school, and then they took us out to the launch pad later. The integration was in September, October, and then the launch was pushed back all the way to early December. But I did get to go to Vandenberg, and the night before the launch, I was allowed to go out to the launch pad, and that's a photo on the right that I took of that Falcon 9 that had our satellite. And the last picture, of course, is a photo from launch, the actual SSOA on 3 December 2018. The image on the right, I actually created that. That is not a real image of our satellite, but it's our satellite over a satellite image of Florida. So that's, let's call that an inspirational photo. And that takes us to the end of our series of mini episodes.
Well, this was not a mini episode, Kevin, but I think it's important to really think about from beginning to end. I mean, you have to understand not only the requirements, what a CubeSat is, and all those parts, the subsystems that go into it, but ultimately that timeline to get there. We could have probably done 3 mini-sodes on these things, one for even one for each one. I think that, you know, someone who's really looking to do a CubeSat would probably want to make sure they have one of those books by their side to really just go step by step.
Well, I can tell you right now, I have some students of varying ages, middle school, high school, and a university student or two. What they're doing right now is they're looking at the reviewers' comments from last year. We applied last year and we were not selected. So they're beginning with the reviewers' comments last year. They're reading the CSLI handbook again, word for word, and we're going to be developing our proposals for this year. So we've already begun the process. We actually started last fall for something we're going to submit a year later. So we are well into the design process, trying to take all of the lessons learned and have a good outcome.
Well, you know, I think for our listeners to understand, you know, at least what a CubeSat is, these little lessons have kind of maybe put those pieces together to really understand why it takes so long, why the fact that middle school students or high school students are building these is such a big deal. It's a commitment that, you know, it is not something that's overnight. So it's a long-term commitment. So anyway, I think I too have learned a lot in the process. So, well, this is going to close, of course, our mini-sodes. We'll be coming back next week, picking up where we left off with our regular interviews. We hope you've enjoyed these lessons. And of course, that you'll join us next week when we say,
let's go to space.